All right, so if you look at the diagrams below or to the right, you got the leptokurtic, the mesokurtic, and the platykurtic. All right. The one that we really want to be closest to would be the mesokurtic. Also, they pronounce it mesokurtic too. It just doesn't. I like to go miso because it sounds like a delicious bowl of miso soup. So that kurtosis is going to tell us the heaviness, or really the texture of the tails of a graph. All right. So the closer it is to the meso, if assuming it's symmetric, it's probably going to be pretty close to a normal distribution. All right. So we have the data in already. So in number 4, it's the same data set, raw data, the V1 values. But yeah, our V2 is going to be pretty funky. So let's go there. Oh, I hit a button. It wasn't a good button. All right. So the heart of this one is just this expression here. Everything else can be done outside of the data editor. All right, so we're really doing essentially the same computation we did before to come up with our list of values. And we find the sum of it, and then we just kind of build around that using the value of n. All right, so it does get a little easier, but we do have to do the typing, and that's why I'm hoping that they can do an upgrade to store in a formula, because this really is it. It's a z-score formula. Although, now that I think about it, I'll check to see if there's a z-score function, because that might even be easier. I'll do that on my own time. So, double open, x minus x bar, so that's v1, shift alpha v1, minus the mean of v1, shift alpha, division 1, close it up, divide. It's the same exact function that we did before, so far anyway. All right, it's the same thing we did before, except we want to just raise it to the 4th power instead. All right, so x to the y, raise it up to the 4th. And then once we do that, we can really essentially just get out of this whole editor, because I need the sum of all these entries, but once I have that, everything else is just rote computation. All right, so I'm going to hit OK. It's going to populate my list. Then I'm going to go to stats, and I'm going to grab the sum value. There it is. It's like 67 and change. Yeah.
Wait, can you see like the formula you put into a table?
Can you, like after you already put it in?
That's also a feature you should download.
Yeah. It'd be nice that if you go back into it afterwards that it's still there. Well, for now, copy paste is the best we got. So next update. So I'm going to go into my home screen, paste it in. Now I'm going to build out the rest of the formula, which seems crazy, but it's really not bad. We're over the hump here, because everywhere you see an n, we're replacing that with 30. So, because there's 30 values in the data set. So I'm going to take this number, multiply it by 30 times 31. Oop, I needed a double paren there. I'm going to divide that by, oh, it's really 29, 28, 27. You could hit OK or execute here if you want, get that answer and subtract the remaining expression from it, or you could just do it all in one shot. So 3 times, that would be 29. The 29 is squared. Then I'm going to divide that by, that's 2827. And that, if you hit enter, gives us our kurtosis value. All right. So the numbers that we're looking for here are really just not as relevant. It's more like, it's just the signs that we care about. So positive, negative, or 0. All right. So my kurtosis value, which with the very creative abbreviation of Kurt, negative 0.461.
Is that like a Greek word?
Was that?
Is that like a Greek word?
Honestly, it's been in my list of things to do to look it up.
Guy named Kurt?
That,
Yeah, I think
that's
it's inspired by Nirvana.
the Kurt Cobain effect, of course. It always keeps returning his head. So we have negative excess kurtosis. So this is platykurtic. Yeah, honestly, I like the beak.
Wait,
Bill,
what's like
Bill,
heavy,
not beak, right?
What's like heavy or light tail mean?
So the best, I mean, I could go verbal on this, but the best I can do is something like that. That's a heavy tail, and this is a light tail.
Wait, so like when it's really like if like the center is higher, then it's lighter.
Not necessarily the center. It has to do with the fringes. So in all cases, you're going to have a horizontal asymptote. They're going to approach the x-axis.
Yeah.
The light-tailed ones approach it quicker. Right? So they get closer to the x-axis quicker than the heavy-tailed. Heavy-tailed is going to take a little longer to get down there. Right. I mean, you can kind of look at it from the perspective of weight distribution, but even that's a little funkier. Right, so yeah, it's just really the distance, or the horizontal distance that it takes for the vertical distance to start behaving like an asymptote.
Wait, so like that diagram, it's like from light to heavy.
Yeah, red is light, black is heavy. And it's an exaggerated drawing, but that's the point, I guess. All right. So then, in terms of doing the other problems, it's really just do the same thing, just type in different data, which can be fun, I suppose. Just maybe not for today. After this, and so I'll just give you a little bit of a breakdown of what we're gonna do, because I'm not gonna make you do the exact same thing all over again today. So we're gonna learn how really to assess normality using techniques other than the empirical rule. And so this is what we're gonna start class on Thursday, determining whether the data set is normally distributed or skewed, but we also need to know the type of kurtosis. All right. So when we get into this graph or this data set, well, one, it's much smaller, so that's great. You know, it's not 30 values, it's like only 9, I believe. And what we're gonna do is we're gonna create what's called a normal probability plot. And that's gonna give us kind of a connection between the different ideas. So if you know how to interpret the normal probability plot, then you can kind of reverse engineer the responses for skewness and kurtosis. But the first thing that we got to do in order to be able to handle that is discover the connection between those three ideas, right? And how, you know, one leads to the other, right? And so you'll see the same set of datas again. That's fun. Same sets of data again, and then this is where we make the connection. And then from there, you'll have a problem that you could work on in groups to determine the nature of the distribution. This is a fun data set. the runs per game for all MLB teams in 2021. Just like, I mean, the concept I think is interesting, but also the way it plays out is kind of cool. And so once you dive into that data, you'll be good.
Do you have nap time last 5 minutes?
Yeah, probably not.